All right, so this will be our last topic on the state of our environment. So, um, just like air pollution, water pollution, and solid waste. So, this will be the last topic regarding that. So, this will be toxic and hazardous waste management. So we know that we also have solid waste management, but generally, toxic and hazardous wastes need to be disposed of or need to be managed in such a way that it will not severely affect our environment. So first of all, what does these symbols mean? So we have this. So what does this mean? So this is what we call the radioactive symbol. How about this one? All right. So this is what we call the biohazard. So in toxic and hazardous waste management, you will be able to see so many of these symbols. All right, so we should be familiar with these. So to start off, hazardous waste is defined as um, ignitable, corrosive, reactive, and toxic. All right. So what is ignitable? So ignitable, it means that hazardous waste is or are substances that can easily catch fire, just like natural gas or alcohol. Next is corrosive. All right. So corrosive are substances that corrode metals in storage tanks and equipment. So usually these are acids or bases. All right. So sulfuric acid and such. Those are corrosive to metals. We also have reactive, so substances that are chemically unstable and readily react with other compounds, often explosively or by producing noxious fumes. All right, so one example of a reactive substance are lithium, which is found in batteries. So lithium reacts with water, producing hydrogen gas, which is also highly flammable and ignitable. We also have toxic substances. So toxic substances, these are substances that harm human health when they are inhaled, ingested, or come in contact with human skin. So examples of which are asbestos, lead, and mercury. So these substances are classified as hazardous waste. So there are also different sources of hazardous wastes, one of which is the industry. So this produces the largest amount of hazardous waste. But in the industry, so industry meaning manufacturing companies, these wastes or their hazardous wastes and disposal is highly regulated. We also have mining and households. So now in households, this is now the largest producer of hazardous waste. So we know in households we have paints, batteries, oils, solvents, cleaning agents, and pesticides. So all of these substances are found in our households. We also have small businesses, agriculture. So in agriculture, we have pesticides as well as fertilizer. We also have utilities and building demolition. So organic compounds, so these are uh, particularly hazardous because their toxicity persists over time. So the toxicity of organic compounds, it stays within the human body over time. All right. So synthetic organic compounds, these resist decomposition, so they stay in the body. If we inhale or ingest it, um, organic compounds takes a long time to decompose. So these synthetic organic compounds, they keep buildings from decaying, they also kill pests and keep stored goods intact. Their resistance to decay causes them to be persistent pollutants. So these do not decompose easily. They are toxic because they are readily absorbed through the skin. Organic compounds also are mutagens, carcinogens, teratogens, and endocrine disruptors. All right. We also have heavy metals. So these are widely used in industry for wiring, electronics, metal plating, pigments, and dyes. So they enter the environment when they are disposed of improperly. These heavy metals are also fat soluble and can break down slowly. So they can, because of this, they can bioaccumulate and biomagnify. So what is bioaccumulation? So it is an increase in the concentration of a chemical in a biological organism over time compared to the chemical's concentration in the environment. So biomagnification is also the process by which substances build up within organisms at each stage of the food chain. So examples of heavy metals, we have lead, chromium, mercury, arsenic, cadmium, tin, and copper. We also have e-waste or electronic waste. So this is the new and growing problem in our society and in our environment today. So these are wastes involving electronic devices. So we have computers, printers, VCRs, fax machines, and cell phones. So these are disposed of in landfills but should be treated as hazardous waste. Some people and businesses are trying to use and reuse electronics to reduce waste. All right, so examples would be the Apple brand. They give out discounts to those who return their old iPhones. So they give discounts to people that return their old iPhones or Apple products in general so that they could buy a new one. All right. So this is part of their initiative to um, regulate e-waste or electronic waste. So there is an illegal dumping of hazardous waste. So since hazardous waste disposal is costly, it results in illegal and anonymous dumping by companies. So if you have seen my introduction, the Love Canal, so that is one of the examples of illegal dumping of hazardous wastes. So this illegal dumping create health risks. Industrial nations illegally dump in developing nations, and the Basel Convention. So this is an international treaty that should prevent dumping, but it still happens. So high costs of disposal encourages companies to invest in reducing their waste, hazardous waste in general. So because of the high cost, so companies are forced to reduce their production of hazardous waste. So there are different disposal methods for hazardous waste. So these methods do nothing to lessen the hazard of these substances, but they help keep the substances isolated from people, wildlife, and ecosystems. So we have the most simple, we have landfills. All right, so these landfills must have impervious liners and leachate removal systems. So design and construction standards are stricter than for ordinary sanitary landfill. So different siya. It has a different design and construction. It also must be located far from aquifers. All right. So as you can see here on this side, this is the illustration of a hazardous waste landfill. We also have surface impoundments. So these store liquid hazardous waste only. So shallow depressions are lined with plastic and clay. Water containing waste evaporates. The residue of solid hazardous waste is then transported elsewhere. The underlying clay layer can crack and leak waste, and rainstorms can overflow, contaminating nearby areas. So this is one of the cons of having a surface impoundment. Lastly, we have the deep well injection. So a well is drilled deep beneath the water table and waste is injected into it. So this is one of the long-term disposal methods. The well is intended to be isolated from groundwater and human contact. However, the wells become corroded and leak waste into the soil. So let's see an example.
The U.S. Environmental Protection Agency has determined that Class II deep injection wells provide the safest method for disposal of oilfield waste fluids. Ohio was granted regulatory authority over Class II and Class III injection wells in 1983 after a U.S. EPA review and determination that Ohio's regulations met or exceeded all U.S. EPA standards. Ohio injection well regulations are written to provide citizens health and safety protections and to minimize environmental risks associated with this oilfield waste disposal method. Ohio enacted updated rules for Ohio's Class II injection wells in January of 2022, updating and enhancing regulations in multiple areas, including increased setbacks, permitting requirements, public notice, construction standards, and more. In the history of Ohio's program, there have been no cases of groundwater contamination caused by the proper disposal of oilfield waste fluids through underground injection. Today, Ohio's underground injection control program is one of the most stringent in the nation. The permitting process is overseen by ODNR experts in geology, hydrology, and seismology. These experts ensure that each well is designed to protect the environment and comply with all Ohio's relevant statutes and rules. Before an order is issued to operate a Class II injection well, ODNR requires operators to provide geophysical logs and tests obtained either during or after drilling of the well. Additionally, ODNR may request an investigation of potential faulting in the immediate vicinity of the proposed injection well, or a plan to monitor any seismic activity in the area. Oilfield waste fluids will be transported to a facility and pumped directly into storage tanks. After allowing time for particulates to settle and after filtration, the resulting fluids are injected deep below the Earth's surface. Spill prevention safeguards are also required at each well site. An underground drain system connected to a sealed concrete vault will be located below the brine truck unloading pad. This serves as a containment vessel if a spill occurs, while the brine hauler is unloading the fluid targeted for injection. The above-ground storage tanks are surrounded by concrete walls or lined dikes that are designed to contain spills. In order to transport oil field waste by truck to an Ohio Class II injection well, brine haulers must be registered, bonded, and insured with the ODNR Division of Oil and Gas Resources Management. The division cannot restrict waste from entering from other states, meaning registered out-of-state brine haulers may transport brine in Ohio to permitted injection wells. In order to ensure Ohio's groundwater is protected, Class II injection wells must have multiple layers of protective steel casings. Each casing is cemented into place. Inspectors from ODNR witness the casing installation and cementing operations to ensure compliance with Ohio's well construction requirements. Geologically, the injection zone for the brine fluid is located below multiple layers of confining rock, which keep the fluids contained in the porous rock formations below groundwater aquifers. Before the injection process begins, a tubing and packer assembly is inserted into the well to monitor for mechanical integrity and to prevent upward fluid movement. Inspectors from ODNR witness the packer installation and the mechanical integrity testing. After receiving authorization to inject from ODNR, brine fluid can then be pumped down the well into the permitted injection formation. Maximum allowable injection pressures are calculated using a formula established in Ohio's rules. By continuously monitoring the pressure of the injection tubing and annular space in the well, ODNR inspectors are able to ensure that mechanical integrity of the well is maintained. Operators are also required to test for mechanical integrity on a regular basis, and ODNR inspects Ohio's injection wells on average 4 to 5 times a year. Once in the permitted injection formation, the confining layers of rock prevent upward movement of the injection fluid. The porous nature of the injection formation allows the injection fluid to be contained below the groundwater aquifers. Through regulation and education, ODNR works to address additional aspects of oilfield waste disposal, such as testing of certain radioactive materials. Ohio law requires testing of certain waste streams for radioactivity and establishes where or how these materials may be disposed. Brine, by law, is not required to be tested for radioactivity when disposed of in a Class II injection well. The Division of Oil and Gas Resources Management has trained radiation safety staff that enforce Ohio's laws and educate oil and gas workers. ODNR recognizes oilfield waste fluids, when not handled properly, pose a threat to our environment and groundwater resources. Through proper application and consistent review of Ohio's stringent regulations, all oilfield waste fluids can be transported and disposed of in a manner that is environmentally safe. The Department will remain vigilant in the pursuit of our mission to ensure a balance between a wise use and protection of Ohio's natural resources for the benefit.
All right, so that was
The
injection
U.S.
well.
Environmental Protection Agency has
Now we also have radioactive wastes. So these are wastes that are particularly dangerous and persistent. So an example would be Yucca Mountain in Nevada. So this mountain is now designated as the single site repository for all U.S. nuclear waste. So the Waste Isolation Pilot Plant is the world's first underground repository for transuranic waste from weapons development. So caverns holding the waste are 655 meters below the ground in a huge salt formation thought to be geological or geologically stable. So the WIP or the WIPP became operational in 1999 and is receiving thousands of shipments of waste. So let's look at this video to see where nuclear wastes go.
When you pass a nuclear power plant in the distance, as you drive down the road, it's impossible not to think about the power that those towering buildings hold. Scientist Enrico Fermi supervised the opening of the first nuclear reactor in 1942, and now our landscapes are dotted by mighty nuclear power plants. These powerful energy plants provide over a fifth of the United States' electricity and don't have the carbon footprint of other energy sources like coal and fossil fuels. So why not build more? One reason: nuclear waste and radioactivity. When managed correctly, nuclear power plants are processing powerful radioactive energy that needs to be disposed of correctly to keep the environment and the people handling it safe. And if someone wasn't handling the planet's safety correctly, like a certain bald bumbler from Springfield, things could go very badly. Dope. The risks of nuclear energy become crystal clear in 1979 in Londonderry Township, Pennsylvania, at the 3 Mile Island nuclear plant. While the reactors were stable, a failure in the mechanical systems regulating the safe venting of gases broke down and allowed a large amount of nuclear reactor coolant to escape. That led to a partial meltdown of Reactor 2, creating a major radiation leak near the city of Harrisburg. A voluntary evacuation of a 20-mile radius around the plant followed. Thankfully, no one in the plant was injured, and later tests showed no increased risk of cancer. But it took 15 years to clean up the surrounding area. It remains the worst nuclear accident in United States history, but is dwarfed by the massive nuclear meltdown at Chernobyl, which caused major casualties and rendered areas surrounding the Ukrainian plant uninhabitable to this day. Given the risks, it's no surprise that nuclear waste and byproducts are strictly regulated by the government. Modern nuclear plants keep waste to a minimum by recycling used fuel back into the uranium-based and mixed oxide fuel. But 4% of nuclear waste can't be processed and remains highly radioactive. Radioactivity is a waiting game, as the toxic quality of the waste decreases over time, measured in half-life, or the time it takes for a radioactive substance to reduce to half of its nuclear value. The time it takes for nuclear waste to neutralize varies wildly. Some common isotopes like strontium-90 have a half-life of around 30 years, but other powerful artificial nuclear isotopes like plutonium-239 have a half-life of over 20,000 years. Not only is it radioactive enough to kill anyone exposed to it, but it could be an unpleasant surprise for whoever digs it up in the far future. Nuclear power plants operate in 31 countries, including all of the world's largest economies, and much of Asia and Africa are planning new builds. The regulation of nuclear waste is overseen by the International Atomic Energy Agency's Joint Convention on Spent Fuel Management, and they work to keep the world safe. The risks of exposure to nuclear waste include higher risk of cancer, higher risk of birth defects in pregnant women, and in high concentrations, organ failure and death. Most nuclear waste comes from nuclear power plants and nuclear arms, but medical and industrial waste and natural radioactive materials also pose a risk. Nuclear waste comes from two main sources: front-end and back-end. Front-end nuclear waste comes from the extraction of uranium and contains radium. The depleted uranium that comes from it is extremely dense and is often recycled into anti-tank shells and other metals where extreme durability is needed. Back-end nuclear waste comes from spent fuel rods and is packed with beta and gamma radiation. These powerful energies come with extremely long half-lives and are formed in nuclear reactors. Some of the most challenging waste to dispose of comes from nuclear weapons materials, and the plutonium used to create these powerful bombs is extremely difficult to separate and isolate. That makes nuclear weapon disposal a growing concern, especially in the aftermath of the Cold War, when the US and Russia drastically slashed their nuclear arsenals. The world is less likely to end now, but what are we going to do with all those things that can end the world? The classification of nuclear waste determines the priority level of the processing and disposal. The lowest priority nuclear waste is uranium mill tailings, which are created by the rough processing of uranium ore. While they don't contain a high level of radioactivity, they have long half-lives and are full of metals with other health risks like arsenic and lead. Low-level waste is the most common waste type because it's anything that came into contact with radioactivity. Common in hospitals and processing plants, it can include paper, clothing, tools, and filters that are used by people working with nuclear energy. These objects pick up trace levels of radioactivity and should be disposed of safely instead of being processed with standard trash. Intermediate waste is usually the byproduct of nuclear processing and is harder to dispose of than low-level waste. Resins, chemical sludge, and metal coverings that have been exposed to nuclear energy long-term pick up the harmful radioactivity, and the hazardous nature builds over time. When breaking down a nuclear reactor for decommissioning, even the building materials surrounding the core can build up radioactivity. Before disposing of this waste, it should be safely shielded to prevent exposure. Then there's high-level waste, and this is what everyone thinks about when they hear about about nuclear power plants. The alarms start blaring, the hazmat suits go on. High-level nuclear waste is as radioactive as you think. But the good news is there are effective ways to contain it. When a nuclear fuel rod serves its purpose and is taken out of the core, it becomes high-level waste. While the number of high-level waste objects is small compared to the other classes, the level of radioactivity is so high that it accounts for over 95% of total radioactivity caused by nuclear energy. While most radioactive isotopes produced by high-level waste are high-powered but have a short half-life, the presence of isotopes like plutonium makes it critical to ensure it's contained safely. So what's the best way to dispose of nuclear waste? That's what nuclear energy-using countries have been arguing over for decades. Most experts say the best solution for long-term disposal is by constructing a deep underground facility similar to a mine that can contain large amounts of high-level waste away from humans and be sealed up in between disposals. But that's easier said than done, and no country has finished one. Although Finland is close to completing their Onkalo spent nuclear fuel repository on the west coast. Currently, countries use a number of alternative systems that are considered safe but imperfect. The first step to minimize the impact of nuclear waste on the environment is to neutralize it as much as possible. This is done by processing it and stabilizing it into a form that loses its explosive properties. Some countries mix the waste with sugar and then calcinate it into a solid object by processing it through a rotating tube. Turned into glass, the waste products are then bonded to the other molecules and then poured into stainless steel and sealed. They're then stored underground, where the waste products are trapped for thousands of years without leaking radioactivity into the environment. Other technologies include ion exchange, where medium-level wastes are neutralized by concentrating the radioactivity into much smaller volumes. This makes them easier to contain, but isn't recommended with the volatile high-level wastes. But when the time range for nuclear waste to become deactivated can reach into the millennia or longer, with some rare isotopes having a half-life of over 1,000,000 years, scientists are concerned that these storage methods can come back to haunt us. That's why we've eliminated many of the more short-sighted methods of nuclear waste disposal, like ocean disposal. Up until the 1990s, many countries, including the United States and the Soviet Union, would dump drums of contained nuclear waste into the ocean, especially in the coastal regions of Somalia. Somalia hasn't had a functioning government since the 1990s, and the pirates weren't going to mess with a large ship bearing a country's flag when they could go after smaller merchant ships. So countries thought anything goes out there. The Arctic Ocean was also a popular choice for the Soviets, as they controlled a huge coast in the north. Overall, 137,000 tons were dumped in the water by European countries in 34 years, and it took its toll on the oceans. Tests of areas where dumping was common found elevated levels of radioactivity, and in 1993, a treaty was passed banning ocean disposal of nuclear waste. The most common current method for nuclear waste disposal is above-ground disposal, where waste is sealed up in a steel cylinder with an inert gas that won't react with it, and then sealed in radiation-shielding concrete. The radiation-proof drums are then sealed in a storage facility near the nuclear power plant. This is how big plants handle their waste in-house, and it's popular for a few reasons. First, it's handled internally and the plant doesn't have to get approval and fight their way through government red tape to find a dumping facility. Second, it's inexpensive and doesn't require construction or expensive materials. Finally, the waste remains on site for reprocessing, which remains the best solution for solving the nuclear waste question. But the secret weapon for eliminating nuclear wastes is chemists and physicists, as these scientists have developed ways to chemically separate fission products and unused uranium from used nuclear fuel. This started by extracting plutonium, with its long half-life, from nuclear fuel to be used in the construction of nuclear weapons. But as the focus shifted from bombs to energy plants, scientists developed ways to create a new type of nuclear fuel from the remnants of the old. MOX nuclear fuel, or mixed oxide fuel, is created in high-level facilities from nuclear waste coming from plants around the country, and has become a top way of disposing of nuclear waste in Europe. In America, the government's focusing on research, and commercial nuclear fuel reprocessing isn't widespread yet. So what will nuclear waste disposal look like in the future? One of the biggest possibilities is space disposal, as this will get the radioactivity as far away from people as possible. The problem, besides the possibility of poisoning some aliens that will come looking for revenge, is that technology isn't there yet. While technology like mass drivers and space elevators is in development, the carrying capacity of our current space shuttles is limited and would only be able to carry a small amount of nuclear waste. The money that goes into every space shuttle launch is high, and the program is far from foolproof. The The loss of the Challenger and the Columbia shuttles proved that a catastrophic accident is possible, and a space shuttle disaster carrying a nuclear payload could contaminate a large area. But could we transform nuclear waste into less harmful waste with a shorter half-life? That was the dream of scientists behind the Integral Fast Reactor, an experimental reactor that would use a nuclear fuel cycle that reprocessed fuel through electro-refining. It would extract almost all the energy contained in uranium, cutting fuel requirements by 2 orders of magnitude. Unfortunately, the design had problems with leaking cooling fluid, and the project was canceled by the US government in 1986. But research is ongoing, and new fission reactors that have much more processing power than the traditional light water reactors are under development now. The Earth itself might be our best ally for disposing of nuclear waste, as man-made structures underground are the top proposal for future storage facilities. By digging out large, stable bunkers in sparsely populated areas of a country, nations could keep their nuclear waste in a centralized location and reduce the risk of leaks happening in multiple locations. Deep borehole disposal is an alternative that creates narrower but much deeper holes capable of storing the waste up to 3 miles under the earth, where any leaks would be far away from humans. The big holdup, besides developing the technology for safe deep earth drilling, getting approval from governments is a holdup. Many countries have rejected proposals out of fears that the disposal won't be safe or that it could destabilize the ground. The consequences of a nuclear accident are massive and long-term, as the residents of Pripyat, Ukraine know all too well. In the heart of the Chernobyl nuclear plant is the Elephant's Foot, a mass of solid nuclear waste caused by the 1986 meltdown. Dense and hard to damage, it was so radioactive when released that it would kill anyone who was in the same room with it. Today, over 30 years later, it's still highly radioactive and poses major health risks to anyone who's exposed. So, however we neutralize our nuclear waste, let's make sure it stays there. Want to learn more about the worst nuclear disaster in history? Watch How I Survived Chernobyl, or check out this video instead. Thanks for watching, and as always, don't forget to like, share, and subscribe.
All right, so that was the nuclear waste management. Okay, so let's move on to managing these wastes through laws and treaties. So we have CERCLA, or the Comprehensive Environmental Response, Compensation and Liability Act. So CERCLA, this is CERCLA 1980. So this is where the Superfund came from. So if you have seen the video that I've posted as an introduction, so you know what Superfund is. So the CERCLA established a federal program to clean up U.S. sites polluted with hazardous wastes. So experts identify polluted sites, take action to protect groundwater near these sites, and clean up pollution. So we have the Superfund program. So experts identify sites polluted with hazardous chemicals, take action to protect groundwater near these sites, and clean up the pollution. So we also have the term brownfields. So these are lands whose reuse or development are complicated by the presence of hazardous materials. So like the introduction that I've shown you, the Love Canal is actually a Superfund site or a brownfield. So the some of the events that spurred the Superfund legislation. So we have the famous Love Canal in Niagara Falls, New York. We also have the evacuation of an entire town in Times Beach, Missouri. So this is after being contaminated with dioxin from waste oil sprayed on roads. So um, this was also uh, one of the events that spurred the Superfund legislation. So the Superfund program, so once a Superfund site is identified, EPA sites, I mean EPA scientists evaluate so how close the site is to human habitation, whether wastes are currently confined or likely to spread, and whether the site threatens drinking water supplies. So this is um, this is one of the signs in a Superfund site by the EPA or the Environmental Protection Agency. So harmful sites are placed on the EPA's national list priority. So um, these are ranked according to the level of risk to human health that they expose or that they pose, cleaned up on a site by site basis as funds are available. So the EPA is required to hold public hearings and inform area residents of its findings and to receive feedback. So dili pwede silang they will declare Superfund sites and not let the people know. So they should be able to conduct public hearings and inform residents. So I think that would be all. Thank you.